So the topic is Pigeonhole Principle. It's known by several other names also. Pigeonhole Principle. Very, very powerful, very simple idea, but extremely powerful idea. It's not a theorem or such, it's just an idea. Okay. And we are going to do it through problems. So the idea will be to do it through problems, and as and when needed, I will say some theory when it's needed. Okay. Like if the topic is number theoretical and I have to say something related to number theory there, then I will say it, or whenever, wherever it's needed, I will say. But we will mostly be doing it through problems. Initially we will, so maybe I can write this. Initially, we will just solve some, some like puzzle type problems. So that maybe we'll do first two classes. But after that, we are going to use this principle to prove some theorems. So there are some theorems, some in number theory I will have, and some in graph theory. But don't worry, basically we will prove some things using this, which you guys will use in many problems, and that's what we call theorems. Yeah. So then you will see the power of this. It's not just to solve puzzles, but also to solve puzzles which themselves are very important. So this will be the plan. Okay. So with that, let us see. Try to do a variety of questions, some of geometric flavor, some of number flavor, and this seed application. So any questions before we start? Okay. No? All right. So then let's look at problem number 1. So you take a number k, okay? Start with, okay, let's start with the number k. Let's say that start with number 2k. Start with the number 2k. Okay. So and so you have to pick. Sorry, you have to pick any k plus 1 numbers. This is just very simple question. So let's see, k plus 1 numbers. Show that at least two will be consecutive. Consecutive, you understand that, one after the other. So you'll pick some t and t plus 1, something like this. To begin with, maybe you can just, so you can say, you can pick 80, and then so from 1 to 80, pick a number 2k, and then you have to pick k plus 1 numbers. So this will be 41 numbers. Okay, so I should say this from 1 to 80, let's say. Or from any 80 numbers. No, so from 1 to 80, sorry. Yeah. Let's do this first. So we're picking k plus, we're picking 41 numbers from 1 to 80. So 80 numbers, and they are 1 to 80, not any 80 numbers. Hmm. No. So you have given one situation in which two of them will be consecutive. Is that right? Like you have given, you're saying that if you pick all the odd numbers, then the 41th number has to be consecutive with one of them. Yeah, so that's not a complete proof. So I can understand this. This looks very obvious. Like this. Is it surprising to anyone? It's not surprising, but yeah, how do we formalize it? So we need to just formalize this. Right? This is obvious, but we need to find a way to formalize it. Obvious, but how to say it? We need to find a model you know to find a way to talk about this so that you can say that two of them. But what are you doing? Adding to, what's the meaning of even numbers? So no, I'm not understanding. Try to say it again on a different way. Maybe. So from the first 80 numbers, we are picking any 41 numbers. That's the thing. You want to show that you will end up picking two of them consecutive. 40 of them which are not consecutive. What does that mean? Yeah, that's not a very well defined set. Right? 40 of them, they are not consecutive. Yeah, but so you're basically saying the same statement. Do you see that? Yeah, so at least that way I can see. So you're trying to say that the largest size subset I can take in which I don't pick any consecutive is 40. But that's the same statement. So come on, someone tell me how do you formalize this? So one of the question that we are doing is, so from the first 80 numbers, you pick any 41 numbers. Okay, you want to show that at least 2 of them will be consecutive. And that kind of seems obvious. In fact, if you pick from any 80 consecutive numbers, if you pick 41 numbers, then 2 of them will be. But how do we show this? And this question is actually sometimes asked in more complicated ways. But right now, we are just in, like, basically trying to learn how to formalize things which are obvious. No, but how to say it. And it's not some deep thing. It's just you need to find a model, find a way to say it, and then do that. So try to partition the numbers from 1 to 80 into pairs maybe, and then show that something, there will be 2 numbers which go in the same pair. Let's see. Since nobody has, so all of us see this, but yeah, let's just see how to make this happen. So the key is to partition the set as. So these are our cages or boxes or pigeonholes, the holes. Oh, I'm making 40 of them, but really I want to capture 2 of them in the same. So the idea is that this will be mark 1 and 2. This will be mark 3 and 4, 5 and 6. So you see what I'm doing. Okay. So these are the homes of those numbers. If I pick the number 1, then I will put it in box 1. I'll put it in the first box. If I pick the number 2, I will again put it in the first box, if I pick it. Okay. So if I pick a number I, then I will pick it in the box in which I is labeled there. Is it fine? So put any picked number in its box. Yeah, I'm having this irritation. That's why I changed the room. Just put any picked numbers in its respective box. You can say this in any way you want. I'm just right. You don't have to say it like this. You can say it's in other words. So this is, I'm just writing for clarity. Then now someone can finish this. So I've given a model like, okay, this is how we are going to. We're doing the same thing, but I'm just arranging it in this way. Yeah, how many boxes do we have? 40 boxes, right? Yeah. Because we only have 40 boxes and we have 41 numbers. So this obvious statement we are ready to agree. Okay. That, I mean, that can also be proved. But then you see that's it. But now we have 41 numbers. Yeah, I can write that now. Just writing the full thing, I think it's for the first time. So now we have 41 numbers. Forty boxes. So 2 numbers will go in the same box, okay, and they will be consecutive. I will not write this later, just first time I'm writing, okay? Because this maybe you can use as a layout, because you have not done proofs earlier, right? So then you can use this. You'll catch it on your own. That's fine. But the idea, okay, the idea in the end is we created a situation where we have 40 boxes and 41 numbers. And so we said the two of them should go in the same box. And they will be considered. Any questions? Now, can anybody tell me, have we proved something more than we needed to prove? I cannot do this on this system. Have we proved something more? So we have shown that at least two numbers will go in the same box. But then you see, our boxes are not all consecutive boxes. They are all consecutive, but they are not all consecutive possibilities, right? Our boxes are like something goes in this. Let's say, yes, we could have done that. Right? But here we are getting something very interesting. We are getting that there will be two numbers which will be consecutive, and the smaller one will be odd and the larger one will be even. That's what we have proved. We have proved a little bit more. Okay, see, this is important. The two consecutive numbers that we will get through this principle, you may get other consecutive numbers. If you just pick from 1 to 41, then you get all kinds of consecutive, right? If you just pick the numbers from 1 to 41, then that. But no matter what you do, you will end up with a consecutive pair in which the smaller one will be even and the smaller one will be odd and the larger one will be even. Okay, two consecutive numbers of the form maybe odd and odd plus 1. Okay, we have proved a little bit more. So these are the things, because you may be asked to prove this. This is the Pigeonhole Principle. Yeah, this the name. And note that we do not know which two consecutive pairs we are going to pick. So this is completely existential. Okay. So that way we are learning that Pigeonhole Principle tells you that something exists, but it never tells you how to find that thing or what is that thing. Or in this problem, it's not even possible to find that thing because you don't know which two consecutive numbers you pick other than this thing. Okay. So we have learned two things here. Okay, we have learned how to model the question in terms of this. So if you think, okay, I have to make what will be my boxes, what will be my pigeons, something like that, maybe then you can model. Okay? You want to show that they can be tracked. That's fine. That you will keep learn more as you do. But the other kind of thing which you learn is you get a sense from the problem whether to apply this kind of principle or not. If the problem is existential, if the problem asks you to prove that something exists, okay. If the problem is, I'm just solving this is wrong language existential, but I'm just saying if the problem is asking you to prove something exists, and you can look at the question and tell, well, I mean, I can prove it exists maybe, but it is not possible to find them. Like in this question, it was not possible to find them. Then a Pigeonhole Principle is mostly the right way. Okay. So the problem is asking to prove something exists, and you know that you cannot really construct it, then it will Pigeonhole Principle kind of idea can be used. Okay, like less space, more objects. You have to partition your space, partition your set in a certain way. Okay, so yeah, that's all right. So any questions so far? Let's go to problem 2. Let's change the flavor. Let's maybe go to a slightly different type of question. Okay. So this is more purely combinatorial. It's about, let's see. So there are 10 people. 10 people at a party. And every person has, some of them know each other, some of them don't know each other. Okay. So some know each other. Obviously, if someone A knows B, then B also knows A that B as well. Some know each other, and some don't. Show that there are at least 2 people. So last column also I should have said at least one consecutive. I should have said at least, but it's not wrong to say just to show that there are 2 people. I'm just saying 2 people. There are 2 people who know the same number of people. Okay. I just say it like this: who have same number of acquaintances. Same number of acquaintances, not the same acquaintances. Okay, who have the same number of so there are 10 people, right? So for example, there are 10 people like this: P1, P2. There are 10 people, and so P1 may know P2, P3, P2. So P2 then knows P1. Let's say P2 doesn't know anyone else. So you see, I mean, it could be a lot of variations. It could be all possible variations. But we still want to show that there are 2 people who have the same number of friends. Same number of friends. There will be 2 people who each have 5 friends, or 2 people each have no friends, or something like that. So this is again similar kind of question, but let's just think. There's no point in saying much. And if you are thinking that you know but you cannot say it, then try to maybe say it for 3 people, 4 people, 4 people at least, not for 3 people. 4 people also, that'll be good. Okay. Let's just put 10.